Have you ever stopped to think about the blueprint of our digital world? Like, what are the deep ideas from way back that make every app, every website, well, work? We talk a lot about figures like Alan Turing, and yeah, absolutely. But there's this other giant, maybe less famous, whose pure abstract thinking really laid down so much critical groundwork. So today we're doing a deep dive into Alonzo Church, an American computer scientist, mathematician, logician, philosopher too. His work from the early 20th century is still shaping things now. Our mission really is to unpack his huge, often kind of hidden contributions. We'll look at his life, his big breakthroughs in math and philosophy, and how his ideas connect directly to the code people write every day. You know, maybe even code you write.
That's exactly right. I mean, Church is absolutely one of the true giants of 20th century logic and computer science. He might not be a household name like Turing, maybe outside of academic circles, but his work isn't just important. It's, well, fundamental to even understanding what computation is.
Okay, so let's start with the man himself. Alonzo Church, born June 14th, 1903, Washington, D.C. And he lived a remarkably long time, passed away in 95, age 92. His academic journey started at Princeton, got his bachelor's in math in 1924, and then boom, PhD right there just 3 years later. His advisor was Oswald Veblen, a big name himself.
Yeah, and his career just shows this incredible intellectual breadth. He taught philosophy and mathematics at Princeton for almost 40 years. That's 1929 to 1967. Then he moved over to UCLA as the Flint professor until 1990. It's pretty unusual, really remarkable to see someone making major contributions across all these fields: computer science, math, logic, philosophy. He just moved between them so naturally.
And his family background is kind of interesting, too, hints at that intellectual side. His dad was a judge, justice of the peace. His grandfather was a U.S. Senate librarian. And his great-grandfather was actually a university president, University of Georgia. There's also a detail, maybe a bit sad. He was partially blinded as a kid, an airgun accident, and he was a lifelong Presbyterian.
Interesting personal notes there.
So with that picture in mind, let's shift to his work. And maybe the most famous piece, the Lambda Calculus. It sounds pretty dense, right? For those of us maybe not dup and cure math, what is the Lambda Calculus, basically? And why was it such a huge deal when he introduced it?
It definitely sounds abstract, but its impact is very, very concrete. The Lambda Calculus, or U calculus, it's a formal system. Think of it like a very minimal, very elegant language just for defining and applying functions, all using symbols. You might see lixm. That just means take an input x and do m with it. And m is just using that rule on an input n. The really profound thing was showing that computation could be boiled down to pure symbol manipulation. No hardware needed, no machine in sight. It was all about the logic.
Wow, okay. Purely symbolic computation. So how does that abstract idea from, the 1930s link up with the code we see or write today? Where's the connection?
Oh, it's everywhere. I mean, really. The Lambda Calculus became the theoretical bedrock for whole styles of programming, what we call functional programming. Languages like Lisp, Haskell, ML, they're built on it. But even if you're not using those specifically, you're still using his ideas. Every single time you write an anonymous function, an arrow function in JavaScript, or a lambda in Python.
Yeah.
That's Alonzo Church's invention, directly. It's what gave us the power to treat functions like flexible little pieces of logic you can pass around, anonymous functions, higher order functions. And then there's the type Lambda Calculus. That's a version with more rules, basically. It formed the foundation for modern compilers and the type systems that make our code safer and more reliable.
So, wait, when I quickly write in JavaScript, that little arrow function, that's Church.
That's Church, absolutely. That conciseness, that flexibility, it flows directly from Lambda Calculus. And those type systems we rely on, the ones that catch errors before you even run the code, that foundational theory comes, in large part, from the type Lambda Calculus. It makes software so much more robust.
That's incredible, just woven right in. Okay, moving on from Lambda Calculus itself, another huge one is the Church-Turing Thesis. You mentioned Turing earlier. This thesis was proposed by both Church, using his Lambda Calculus, and Turing, with his Turing machines, right? Independently.
Yes, independently, which is fascinating in itself. And this thesis is, well, I don't think it's an exaggeration to call it the bedrock principle of computer science. It essentially claims that any function you can effectively compute anything that could, in principle, be calculated by a step-by-step mechanical procedure can be computed by a Turing machine, or equivalently by the Lambda Calculus.
So it defines the limits, like what's possible for computers to do.
Precisely. It sets the boundary. It tells us what computable even means in a rigorous way.
Yeah.
Before Church and Turing, the concept was, frankly, a bit fuzzy. Their work gave it a precise mathematical definition. It basically defined the entire field of theoretical computer science. Without it, understanding the limits of computation would have been much harder. Decades harder, maybe.
Got it. A universal definition of computation. Now, I also read about his proof related to the Entscheidungsproblem, the decision problem. What was that about?
Right, the Entscheidungsproblem. This is a famous challenge posed by Hilbert, asking for a general algorithm, a procedure that could take any statement in first-order logic and decide if it was universally valid, basically true or false. Church, using his Lambda Calculus, proved that no such general algorithm could possibly exist. This result is known as Church's theorem.
So no universal truth decider for math.
Exactly. And what's really interesting is that his proof actually came out slightly before Alan Turing published his famous proof about the halting problem, which is another angle on the same fundamental limitation of computation.
Wow. So he beat Turing to that punch, in a way.
In terms of proving the unsolvability of the Entscheidungsproblem using his formalism, yes. He also used Lambda Calculus to show that P arithmetic, sort of the basic rules of numbers, is undecidable, meaning there's no single algorithm to decide the truth of all statements within it. And he also co-developed the Church-Rosser theorem, which is technically important for ensuring the Lambda Calculus itself behaves consistently.
Beyond these specific breakthroughs, he was clearly deeply invested in the field itself, founding editor of the Journal of Symbolic Logic, editing the reviews for 43 years. That's dedication.
Incredible, isn't it? 43 years shaping how symbolic logic was reviewed and discussed. And he wrote a major textbook, Introduction to Mathematical Logic, known for being incredibly precise, meticulous. So his influence wasn't just brilliant ideas, but also building the community and the standards of the field.
Right. Now, you mentioned he taught philosophy too and worked across disciplines. What about his philosophical work? What does all this logic and computation mean for philosophy?
That's a great question. His philosophical contributions are significant, especially in philosophy of language and logic. He championed what's called the logistic method, applying formal logic rigorously to philosophical problems. He was a strong critic of nominalism, the view that abstract things like numbers are just names, and a defender of realism, believing these abstract objects genuinely exist.
Okay, realism about numbers and logic.
Exactly. And maybe one of his most discussed philosophical arguments is the slingshot argument. It's a clever, technical argument suggesting that the thing a sentence refers to isn't some complex idea or proposition, but simply its truth value, whether it's true or false.
Whoa. So the meaning or reference boils down to just true or false.
That's the core idea of the argument, yeah. It was a really influential, if controversial, idea in logic and philosophy of language. It connects to his work on the Frege church ontology, which builds on Gottlob Frege's ideas about sense and reference.
Mind-bending stuff. And his influence wasn't just his own writing, right? You mentioned students earlier. He supervised 31 PhDs.
Yes, 31. And the list of his students reads like a who's who of 20th century logic and computer science. We mentioned Alan Turing, of course, but also Stephen Kleene, J. Barclay Rosser, who he worked with on the Church-Rosser theorem, Dana Scott, Martin Davis, Leon Hankin, Michael O'Rabin, Raymond Smullyan. These are foundational figures in their own right.
Turing was actually his PhD student at Princeton.
Yep, from 1936 to 1938. Turing came to Princeton specifically to work with Church, and his own PhD thesis famously extended Church's ideas on computability, essentially solidifying the Church-Turing Thesis we talked about. That collaboration, that mentorship was hugely significant.
It really shows the power of mentorship. And it wasn't just direct students. Others were influenced too, like Haskell Curry.
Right. Haskell Curry, another major logician, expanded on Church's ideas. The concept of currying in programming, transforming a function that takes multiple arguments into a sequence of functions that each take a single argument, is named after Curry, but deeply related to the functional ideas Church pioneered. The ripples just keep spreading.
So when you pull it all together, what's the enduring legacy?
It's immense. Church's frameworks, especially Lambda Calculus, are the absolute bedrock for functional programming, as we said, but also for formal verification, proving software is correct, for proof assistance, tools that help mathematicians check proofs, for type theory, compiler design. If you think of Turing as maybe the visionary of the physical machine in AI, Church is the pure logician who gave us the abstract language of computation.
So the language itself.
Exactly. Yeah. Together, they really defined what it means to compute from both the abstract and the more concrete perspectives.
And he certainly received recognition for it, elected to the American Academy of Arts and Sciences, the National Academy of Sciences, honorary doctorates, too.
Yes, from places like Case Western Reserve, Princeton itself, University of Buffalo. His contributions were definitely recognized within the academic world. And, maybe fittingly, there's now the Alonzo Church Award for outstanding contributions to logic and computation. It was established in 2015. It ensures his name and his foundational impact continue to be honored by new generations.
It really is amazing to think how these deeply abstract theories from decades ago form the foundation of the very concrete digital world we use every single day, from the core understanding of computation limits right down to the syntax of the code people write. His fingerprints are kind of everywhere, even if you don't see them directly.
Absolutely. It's not just dusty academic history. It's alive, embedded in the software we use, in how we think about problem solving with computers. Without church, computer science, programming, it would all look very, very different. Almost unrecognizable, maybe.
So maybe the next time you use an app or write a bit of code with an anonymous function, or even just hear about AI pushing the limits of computability, maybe take a second to think about Alonzo Church, the quiet logician whose abstract thoughts gave us the language for it all. Makes you wonder, doesn't it? What other sort of invisible giants are out there now, shaping the foundations of whatever comes next?